Our universe is stretching apart faster than it should. This is not a small error, but a fundamental crisis called the Hubble Tension, one of the greatest mysteries in all of science. By the end, you will understand the 25 compelling reasons why this single number threatens to rewrite the rules of our cosmos. The very tools we use to measure the cosmos might be lying to us, or something unknown is tugging at the fabric of reality. What do you think is really out there shaping our universe? Our cosmic measuring tape is breaking. To grasp the full scale of the Hubble tension, you first need to understand the tools scientists built to map the heavens, a delicate structure known as the cosmic distance ladder. Think of it as a staircase leading from our own galactic neighborhood out to the edge of the observable universe. Each step or rung relies on a different kind of celestial object with a known brightness, a so-called standard candle. The first rung might be a pulsating star called a Cepheid variable, whose steady rhythm of brightening and dimming reveals its true luminosity. By comparing how bright it actually is to how dim it appears from Earth, astronomers can calculate its distance with stunning precision. Then they use these nearby Cepheids to calibrate the next rung, often type 1 a supernova. These are colossal stellar explosions that always peak at the same intrinsic brightness, making them brilliant beacons visible across vast cosmic voids. By carefully climbing this ladder, rung by rung, scientists measure how fast galaxies are moving away from us right now in our local universe. But here is where the trouble begins. When they finish this painstaking climb and get a number for the expansion rate, it stubbornly disagrees with the prediction from the afterglow of the Big Bang. It is like using two different kinds of rulers to measure the same room and getting two different answers. The local measurement says the universe is expanding faster, significantly faster than the ancient light from the cosmic dawn says it should be. This is not a minor rounding error. It is a fundamental misalignment in the very foundation of how we measure everything, suggesting that perhaps our best tools for seeing the cosmos are not just imperfect, but are actively misleading us about the true nature of reality. What if the ladder itself is built on shaky ground? This pristine snapshot from the dawn of time gives us our second and perhaps most profound reason for the tension. The cosmic microwave background, or CMB, is the oldest light we can see, a fossilized echo of the Big Bang itself. It is a baby picture of the universe captured when it was a mere 380,000 years old. The European Space Agency's Planck satellite mapped this afterglow in exquisite detail, revealing tiny temperature fluctuations that are like the cosmic blueprint for everything that followed. From this single ancient image, scientists can run the cosmic film forward. They can plug the properties of this infant universe into our most trusted model of cosmology, and it predicts with stunning certainty how fast the universe should be expanding today. This is not a guess, it is a precise calculation based on the fundamental laws of physics. Yet when we look up at the modern cosmos, when we measure the actual, live expansion rate using galaxies and supernova, the number we get is significantly different. The universe today is simply not behaving the way its own baby picture says it should. We are left with a bewildering conflict between two of the most trusted pillars of modern science. One is the pristine, theoretical prediction from the universe's birth. The other is the direct, observational measurement of its current state. Both cannot be correct. So which one is lying, the ancient echo or the modern sky? Could there be a subtle crack in the very foundation of our cosmic blueprint? This leads us to the third compelling reason the Hubble tension is so puzzling: the unsettling possibility that our measurement of the cosmic microwave background itself is flawed. We have treated this ancient light as an infallible record, a perfect snapshot of the infant universe. But what if our reading of this snapshot is mistaken? The Planck satellite provided an immense amount of data, and untangling its signals required incredibly complex models and data processing. scientists must carefully subtract the foreground glow of our own Milky Way galaxy, account for the dust between stars, and model the precise physics of how light and matter interacted in that primordial soup. A tiny, unknown systematic error buried in any one of these steps could subtly skew the final result. It is like trying to hear a whisper in a crowded, noisy room. You might mishear a crucial word. Perhaps our models of the CMB physics are incomplete. What if there is some unknown particle or interaction from the early universe that left a faint imprint on the light, an imprint we do not yet know how to decode? We assume we understand the simple ingredients of the early cosmos perfectly, but what if the recipe had a secret spice we have not yet tasted? If our interpretation of this cosmic fossil is even slightly biased, then the prediction for today's expansion rate would be fundamentally wrong. The tension would not be a mystery of the cosmos, but a mistake in our own cosmic translation. So we are forced to ask a deeply uncomfortable question. Are we truly reading the universe's baby picture correctly, or are we seeing what we expect to see, missing a crucial detail that changes everything? Perhaps the most profound answer lies not in our measurements, but in our models. We are forced to confront the possibility that our entire understanding of the universe's infancy is incomplete. What if unknown physics, forces or particles we have not yet discovered, were at play in the first fleeting moments after the Big Bang? Our standard model of cosmology is built on a robust foundation, but it might only be an approximation of a much stranger and more complex reality. Imagine a master clockmaker building a beautiful, intricate timepiece. We have studied the finished clock for decades and think we understand its every gear and spring. But what if, in the very first seconds of its assembly, the clockmaker used a hidden tool or applied a mysterious pressure that subtly altered its inner workings? The clock still ticks, but it runs at a pace we cannot fully explain using only the gears we can see. In the same way, something exotic could have tampered with the cosmic engine in its first instance. Perhaps a new type of dark energy, far more potent than the kind we see today, gave the universe an extra push in its youth. Or maybe there was an unexpected interaction between dark matter and radiation, a brief cosmic tug of war that changed the initial conditions just enough. These early moments set the stage for everything that followed. A tiny tweak to the universe's initial expansion rate would propagate forward through billions of years, culminating in the mismatch we observe today. The Hubble tension, then, would not be an error but a fossil. It is the lingering echo of a forgotten law of physics, a ghost in the cosmic machine waiting to be discovered. Are we on the verge of uncovering a deeper layer of reality, one that was only visible in the universe's first breath? The very force driving the universe apart might be changing its mind. For decades, our best model has treated dark energy as a constant, an unchanging pressure woven into the fabric of empty space itself. This simple idea, called the cosmological constant, has been a cornerstone of modern cosmology. But what if this cornerstone is cracking? This leads us to the fifth and deeply unsettling reason for the Hubble tension. The possibility that dark energy is not constant at all, but a dynamic force whose strength has evolved over the vast history of the cosmos. Imagine a rocket engine that is supposed to fire at a steady, predictable thrust. You calculate its trajectory based on that constant power, but if that engine's thrust has been secretly increasing over time, the rocket would end up far ahead of its predicted position. The universe might be doing the same thing. The local measurements, which show a faster expansion, could be a sign that dark energy's push has grown stronger in the recent cosmic era. The ancient light from the CMB, however, reflects the average strength of this force over billions of years. If dark energy was weaker in the past but is stronger now, it would perfectly explain why the two measurements do not match. The local universe feels the full force of this newly invigorated push, while the ancient light remembers a time when the push was gentler. This is not a small adjustment. It would mean that our fundamental understanding of the universe's dominant component, the very thing dictating its ultimate fate, is fundamentally wrong. Instead of a simple, static background energy, we might be dealing with something far more complex and alive, a cosmic actor that has been playing a different role all along. What if the engine of the cosmos is not just running but accelerating, but our universe is filled with more than just dark energy and dark matter? It is teeming with ghostly particles that barely interact with anything at all. This brings us to the neutrino wildcard. Billions of these elusive particles, born in the Big Bang and in the hearts of stars, are streaming through you every second, utterly unnoticed. For a long time, we thought they were massless, zipping through the cosmos at the speed of light and having little lasting impact on its structure, but we now know that is wrong. Neutrinos do have mass, an astonishingly tiny amount, but we do not know exactly how much, and in the delicate balance of cosmic evolution, even this faintest whisper of mass can tip the scales. Think of the early universe as a vast, still pond. The gravitational tug of every single particle, no matter how light, creates ripples on this pond. Neutrinos, with their slight but real mass, would have subtly changed the pattern of these ripples. They would have smoothed out some of the tiny lumps in the early universe that eventually grew into galaxies and clusters. This smoothing effect would have altered the blueprint imprinted on the cosmic microwave background. If our models assume the wrong mass for neutrinos, then our prediction for how fast the universe should be expanding today is also wrong. It is like trying to predict the final shape of a tree by studying its seed, but not knowing the exact strength of the gravity that will pull its branches down. We are missing a crucial variable. Could it be that there are more types of neutrinos than the three we know, or that their masses are fundamentally different from our best guesses? This uncertainty is a hidden lever in our cosmic equations. A small adjustment here could resolve the tension, revealing that these cosmic ghosts have been quietly shaping the destiny of the universe all along. Even our cosmic shortcuts are giving us conflicting directions. Another independent method for measuring the expansion rate uses the universe itself as a giant magnifying glass through a phenomenon called gravitational lensing. When a massive galaxy cluster sits directly between us and a distant quasar, its immense gravity bends and distorts the light, often creating multiple images of that single quasar around the cluster's edge. Because the light for each image takes a slightly different path around the gravitational obstacle, the images do not all flicker and change in brightness at the same time. There is a tiny, measurable delay between them. By meticulously tracking these time delays, astronomers can geometrically triangulate the distances involved and calculate a completely independent value for the Hubble constant. Yet this powerful technique often produces a number that lands in a deeply confusing place. It does not firmly side with the faster local measurement, nor does it confirm the slower prediction from the ancient cosmic microwave background. Instead, it frequently lands right in the messy middle, straddling the divide in a way that satisfies no one. This is not a clear verdict, it is a third, ambiguous voice entering the debate. It is as if you asked three expert navigators to chart the same course. One uses a detailed map from the journey's start, another uses landmarks seen today, and this third uses the echoes of their own shouts bouncing off distant canyon walls. All three are respected experts, yet all three insist on a slightly different path forward. The lensing results deepen the mystery because they come from a completely different chain of reasoning and observation. If they consistently agreed with one side, we might have a clear winner, but their stubborn refusal to pick a side suggests that the problem is even more fundamental than we feared. Perhaps our very understanding of gravity, or the nature of the lensing galaxies themselves, contains a hidden flaw. This independent anomaly confirms that the Hubble tension is not a simple two-sided argument, but a multifaceted puzzle where every new piece of data seems to add more questions than answers. Our cosmic neighborhood is not perfectly still. While the universe as a whole is expanding, our own galaxy, along with its neighbors, is also swimming through space, pulled by the immense, invisible tendrils of the cosmic web. This local motion is known as a peculiar velocity, and it is the eighth critical reason the Hubble tension remains so stubborn. When we measure a distant galaxy's speed, we are not just seeing the clean stretch of cosmic expansion. We are seeing that pure expansion plus any extra shove or drag from these local gravitational currents. It is like trying to measure a steady river current while you and your measuring boy are both caught in a swirling local eddy. To get the true speed of the river, you must first subtract the motion of the eddy. Astronomers face the same painstaking task. They must calculate and remove the influence of our Milky Way's own journey, which is being tugged by the great attractor and repelled by the dipole repeller, vast gravitational structures in our intergalactic vicinity. The concern is that these peculiar velocities might be significantly stronger and more complex than our models predict. If we underestimate this local churning, then we are misinterpreting the data. A galaxy that seems to be flying away from us at a certain speed due to cosmic expansion might actually be moving slower, with its apparent speed boosted because it is also being tugged toward a nearby supercluster we have not fully accounted for. This would mean our local measurement of the Hubble constant is artificially inflated, creating a false tension with the pristine prediction from the cosmic microwave background. The question becomes a profound one. Is the tension real, or is it simply a reflection of our own messy, complicated, and not fully understood place within the cosmic architecture? Are we trying to read the grand story of the universe while still trapped in a single, noisy paragraph? Our local cosmic address might be far more unusual than we ever suspected. What if the entire Milky Way galaxy, along with our neighboring galaxies, resides inside a vast and underdense region of space, a cosmic void often nicknamed the Hubble bubble? This is not a void of complete emptiness, but a colossal sphere where the average density of galaxies and matter is significantly lower than the rest of the universe. The implications for the Hubble tension are profound. In a less dense region, the gravitational pull holding things together is weaker. The fabric of space-time within this bubble would expand more freely, like a patch of rubber sheet with less weight on it, stretching faster than the more crowded universe outside. When we measure the expansion rate using nearby supernova and galaxies, we are measuring this faster local stretch. We are, in effect, taking a speed reading from inside a special, accelerating zone and assuming it represents the entire cosmos. But if we are living in a cosmic backwater, our local measurement is an outlier, not the global average. The prediction from the cosmic microwave background, on the other hand, gives us the true, overall expansion rate for the universe as a whole. The tension, then, would be an illusion, a grand cosmic sampling error. We have been fooled by our own unusual location. The idea is controversial because it suggests our place in the cosmos is not just ordinary but remarkably special. Most cosmological models are built on the principle that the universe is roughly the same everywhere when you look at large enough scales. To be sitting in a void large enough to cause this discrepancy would be incredibly unlikely, like a single grain of sand on a beach finding itself in the only dry spot for miles. Yet, if true, it would resolve the Hubble tension without requiring any new physics at all. It would mean the problem is not with the universe's laws, but with our perspective. Are we cosmic hermits living in a quiet neighborhood and mistakenly thinking the whole city is as calm as our own street? Our most trusted cosmic beacons might be flickering with hidden flaws. For decades, Type 1, a supernova, have been the gold standard for measuring the vast distances to far-off galaxies. These titanic explosions occur when a white dwarf star steals just enough matter from a companion to cross a critical weight limit, triggering a thermonuclear blast so predictable it always peaks at the same intrinsic brightness. This consistency is what makes them perfect standard candles, or so we thought. The 10th reason the Hubble tension endures is the growing suspicion that this foundational assumption itself could be wrong. What if these cosmic bombs are not all built from the exact same blueprint? The progenitor systems, the specific dance of two stars that leads to the explosion, might have subtle variations. One supernova could come from two white dwarfs spiraling together and merging. Another might be a single white dwarf slowly siphoning gas from a giant red star. These different paths to destruction could produce explosions with slightly different peak luminosities. A supernova born from a merger might be inherently brighter than one from a simple accretion event. If we calibrate our entire cosmic distance ladder assuming they are all identical, we are making a critical error. It is like assuming every single light bulb in a city is a 100-watt bulb. If some are actually 90 watts or 110 watts, your map of the city based on their apparent brightness will be profoundly distorted. A supernova that appears dim might actually be a 90-watt bulb that is closer, but we would mistake its dimness for being farther away. This miscalculation would directly throw off our measurement of the expansion rate. We might think galaxies are fleeing faster than they truly are because we are misjudging their distances. The pristine prediction from the cosmic microwave background remains untouched by this potential error, creating the very tension we are trying to solve. Could it be that the key to this cosmic mystery is not in the fabric of space-time, but in the imperfect nature of the stellar explosions we use to map it? Even the steady pulse of our cosmic metronomes might be betraying us. Cepheid variable stars have long been the trusted foundation of the cosmic distance ladder, their rhythmic brightening and dimming providing the first crucial step into the wider universe. But these celestial lighthouses are not all built from the same stellar material. A Cepheid's pulse is directly tied to its intrinsic brightness, a beautiful and reliable relationship. However, that relationship can be subtly influenced by the star's chemical composition, specifically its metallicity, which is the amount of elements heavier than hydrogen and helium it contains. A Cepheid born in a region rich with these heavy elements will have a slightly different pulse and brightness compared to an identical star formed in a more pristine, metal-poor environment. If we fail to account for this, we are misreading the very first step on our staircase to the cosmos. The problem deepens when we look toward crowded stellar cities like the dense cores of distant galaxies. Here, the light from a single Cepheid can easily blend with the glow of neighboring stars. It is like trying to pick out one specific voice in a roaring stadium crowd. The signal gets contaminated. This blending makes the star appear brighter than it truly is, leading us to believe it is closer than it actually is. And then there is the matter of our cosmic ruler itself, the Gaia spacecraft. This incredible mission is building a three-dimensional map of our galaxy by measuring the positions and distances of over 1 billion stars with unprecedented precision. We use Gaia to calibrate the nearby Cepheids, locking in their true distances. But what if Gaia's own measurements, especially for the most distant Cepheids used in this calibration, carry their own tiny, hidden uncertainties? Any slight error in this fundamental calibration propagates upward, shaking the entire ladder. A miscalibration of just a few % at the first rung becomes a significant divergence by the time we reach the top, where we measure the expansion of the universe. So the question we must confront is terrifying in its simplicity. Is the Hubble tension a sign of new physics, or is it merely a reflection of a wobble in the very first step we take to measure our universe? Our entire view of the cosmos rests on the reliability of these pulsating stars, and now we are finding their beat might not be as steady as we once believed. Our universe is not a smooth, featureless soup. It is a vast cosmic web, a tapestry woven from immense filaments of galaxies, sprawling empty voids and dense, glittering clusters. This grand architecture, the large-scale structure of everything, presents the 12th profound reason the Hubble tension persists. What if the universe's expansion rate is not a single universal number, but a local experience that depends on where you are standing? We assume that on the largest scales, the cosmos is homogeneous and isotropic, meaning it looks roughly the same in every direction and from every point. This cosmological principle is a bedrock of our models, but the cosmic web challenges this simplicity. Think of the universe as a mountain range. If you are standing deep in a valley, your view is limited and the local terrain slopes down around you. If you are on a high peak, you see for miles in every direction. Now, imagine that gravity makes the valley sink a little faster and the peaks rise a little slower. An observer in the valley would measure a different local rate of landscape change than an observer on the peak. In our universe, the dense clusters and filaments are the mountains, their immense gravity pulling inward and resisting the expansion of space. The vast, empty voids are the valleys where, with less matter to hold it back, space itself can stretch faster. When we measure the Hubble constant from our position in the Milky Way, we are not getting a perfect average of the whole cosmos. We are taking a local sample, a measurement that is inevitably filtered through the specific configuration of galaxies and voids that surround us. If we happen to be in a region that is slightly less dense than the true cosmic average, our local expansion measurement will be slightly faster than the global rate. The prediction from the cosmic microwave background, however, gives us that true, smooth, average expansion rate for the entire universe, so the tension might simply be a reflection of our own place within the cosmic geography. We are not at the center of the universe, but we might be in a slightly underdressed neighborhood, and that subtle bias could be the source of all this conflict. Is the Hubble constant not a constant at all, but a cosmic postcode, a number that changes depending on your address in the great celestial city? Einstein's theory of gravity has passed every test we have thrown at it for over a century. From the bending of starlight to the precise orbits of Mercury, general relativity has been our unshakable guide to the cosmos. But this 13th reason for the Hubble tension asks a truly radical question. What if this brilliant theory, our masterpiece of physics, is not wrong but merely incomplete? What if it begins to fray at the very edges of the observable universe? Our entire understanding of cosmic expansion is built upon the equations of general relativity. They tell us how matter and energy should curve space-time, and how that curvature should dictate the rate at which universe stretches. The prediction from the cosmic microwave background relies entirely on this framework, yet our local measurements of the expansion seem to be disobeying it. This is not a small disagreement. It is a fundamental mismatch that suggests the rules of gravity might operate differently on the largest imaginable scales. Imagine you have a perfect map of your city. It guides you flawlessly through every neighborhood and street. But one day you drive to the very edge of town to a vast open plain, and your map suddenly becomes unreliable. The distances no longer add up and the directions lead you astray. You would not throw the map away, it is still perfect for the city, but you would realize it was never designed to describe the wilderness. General relativity might be our perfect city map. It works impeccably within galaxies and clusters, but when applied to the entire cosmos, to the immense, smooth expanse between superclusters, a subtle correction might be needed. Perhaps gravity weakens slightly over these vast distances, or maybe the fabric of space-time has a property we have not yet accounted for, a kind of cosmic friction that changes how it expands. If our theory of gravity is subtly modified, the predicted expansion rate from the early universe would change, potentially snapping into perfect alignment with what we see today. The Hubble tension would then be the first observable crack in a century-old pillar of physics, a sign that we are finally glimpsing the limits of Einstein's universe and stepping into a new, uncharted gravitational frontier. Are we on the verge of a revolution that will not just explain a number, but redefine the very force that holds reality together? Perhaps the universe's first moments were shaped by a phantom force, a fleeting presence that vanished before leaving any obvious trace. This brings us to a compelling and highly specific idea known as early dark energy. Imagine the cosmos in its infancy, a seething, opaque plasma of particles and light. In our standard story, this plasma had a certain density and pressure, which determined how far sound waves could travel through it before the universe became transparent. This travel distance, the cosmic sound horizon, became the fundamental ruler etched into the cosmic microwave background, the very standard we use to predict today's expansion rate. But what if, for a brief, explosive period before that moment of transparency, an extra form of dark energy flooded the cosmos? This would not be the dark energy we know today, but a transient, potent burst of repulsive gravity that temporarily dominated the universe. Its sudden push would have made the infant cosmos expand just a little bit faster during that critical window. Think of a sprinter who gets an extra, powerful shove right at the starting block. For a few moments, they surge ahead faster than expected, but then the push vanishes and they continue running at their normal, powerful stride. The effect on the cosmic sound horizon would be profound. In a faster expanding medium, sound waves cannot travel as far. The cosmic ripples would have a shorter distance to spread out before the universe cleared, freezing their pattern into the CMB. So we would measure a smaller sound horizon scale in the ancient light. Our current models, which assume no such early push, look at that smaller ruler and mistakenly infer a slower expansion rate for the modern universe. But if we correct the model to include this brief, early dark energy episode, the smaller ruler makes perfect sense. The prediction for today's expansion rate would then jump upward, aligning beautifully with the faster rate we measure in our local neighborhood. The Hubble tension would simply vanish. This elegant solution suggests that dark energy is not a constant, but a dynamic actor that can come and go, its influence waxing and waning across cosmic history. It hints that the vacuum of space itself might have phases like water turning to steam, and that we are only now beginning to perceive the echoes of its first, most dramatic transformation. The cracks are not just between past and present, they are forming within our modern measurements themselves. We have been speaking of the Hubble tension as a single, clean battle between two opposing sides, the ancient universe versus the modern one. But a closer look reveals a splintering conflict, a troubling maze of inconsistencies right here in our own cosmic backyard. Even the different methods we use to measure the local expansion rate are starting to disagree with each other. It is a tension within the tension, suggesting the problem is far more layered and complex than we ever imagined. Take the two primary pillars of the local measurement. One relies on the classic cosmic distance ladder, climbing from Cepheid variable stars to Type 1, a supernova. This method consistently gives us a higher, faster value for the Hubble constant. But another powerful technique uses the physics of merging neutron stars, events that create both gravitational waves we can detect and a flash of light we can see. By analyzing the properties of these cosmic collisions, astronomers can bypass the traditional ladder entirely and measure the expansion rate in one single, elegant step. And this independent method often produces a number that is lower, slower, and closer to the prediction from the ancient cosmic microwave background. So now we are faced with a bizarre triangle of disagreement. The ancient light says one thing, the supernova distance ladder says another, and the gravitational wave standard sirens whisper a third, different value. It is as if you asked three master chefs to prepare the same recipe using the same ingredients, and each one produced a completely different dish. This internal strife is perhaps more alarming than the original tension itself. It tells us that the issue is not simply a choice between an old prediction and a new observation. The very tools in our modern toolkit are giving us conflicting answers. This could mean that our understanding of the supernova method is flawed in a way we do not yet see, or that our models of neutron star mergers contain a hidden error. Perhaps the universe is not just expanding at a surprising rate, but that the rate itself appears different depending on which cosmic messenger you ask to measure it: light, gravity, or the echoes of stellar explosions. The mystery has deepened from a simple disagreement into a multifaceted puzzle where every path forward seems to lead to a new, more confusing crossroads. We pinned our hopes on a technological marvel, a telescope so powerful it could see the first starlight of creation. The James Webb Space Telescope was built with the Hubble Tension in mind, its golden eye designed to stare down the cosmic distance ladder and find the flaw. Its mission was one of ultimate precision, to observe the same Cepheid variable stars and supernova with a clarity Hubble could only dream of, finally ending the debate. Yet its initial results have not brought peace, they have thrown fuel on the fire. Webb has confirmed with staggering certainty the measurements from the local universe. The Cepheids it observed, free from the contaminating light of crowded galactic cores, have solidified the rungs of the distance ladder. There is no significant error in the local measurement. The universe really is expanding at this faster rate right now. This should have been a triumphant moment, a vindication of one side of the argument. Instead, it has only deepened the mystery. By eliminating one of the most plausible sources of error, the calibration of the cosmic distance ladder, Webb has slammed the door on a simple fix. The telescope built to solve the crisis has instead authenticated the crisis itself. We are left with a more unsettling reality than before. The problem is not in our instruments, it is in our physics. The James Webb Space Telescope has handed us a verdict, not an answer. It has told us with its cold, impeccable data that the tension is real. The conflict between our local universe and its ancient echo is not a measurement error, it is a fundamental feature of the cosmos. So we must now ask, with a new and more profound urgency, what secret is the universe keeping from us? This number is not just a measurement, it is a direct challenge to our most complete story of the cosmos. The standard model of cosmology, known as lambda CDM, is a masterpiece of modern physics. It is a precise and elegant mathematical framework that describes a universe made of about 5% ordinary matter, 27% dark matter, and 68% dark energy, the lambda. This model has predicted the existence of dark matter, the distribution of galaxies, and the subtle patterns in the cosmic microwave background with breathtaking accuracy. It is the bedrock upon which we have built our entire understanding of the universe's history and fate. But the Hubble constant from local measurements is now hammering at that bedrock. The value is simply too high. It sits stubbornly outside the range that the pristine lambda CDM model, fed by the data from the early universe, will allow. Think of it as a perfect sealed archway. The ancient CMB data gives us the shape and size of one side of the arch, and lambda CDM defines the perfect curve that must connect to the other side, predicting the expansion rate today. The local measurement, however, is like a keystone that is too large. It does not fit the elegant curve. You cannot simply force it into place without cracking the entire structure. To make the high local value work within the model, you would have to start bending its core parameters to their breaking point. You would need to tweak the amount of dark matter, or change the behavior of dark energy, or alter the number of neutrino species in ways that would break the model's beautiful agreement with all the other data we have. It is a zero-sum game. Fixing the Hubble tension by force would create new, equally severe tensions elsewhere. The persistence of this high value is not just an anomaly, it is a systemic failure. It suggests that lambda CDM, for all its monumental success, might be an incomplete picture. We are being told by the universe itself that our cornerstone model, the very foundation of modern cosmology, is missing a crucial piece. What fundamental ingredient did we leave out of our recipe for reality? The very ruler we use to measure the cosmos might be shrinking. This 18th reason strikes at the heart of our predictive power, focusing on a fundamental standard etched into the ancient light, the cosmic sound horizon. In the universe's first few 100,000 years, it was a hot, dense soup of particles and light, a plasma so thick that photons of light could not travel freely. They were trapped, constantly bouncing off free electrons, creating a pressure that sent powerful sound waves rippling outward through the primordial fluid. These were not gentle whispers, but colossal tsunamis of compression and rarefaction racing through the newborn cosmos. Then, in an instant, the universe cooled enough for atoms to form. The electrons were suddenly captured, the plasma cleared, and the universe became transparent. The light, which had been trapped for so long, was finally released, streaming out in every direction to become the cosmic microwave background we detect today. But those sound waves were frozen in place at that exact moment, their farthest reach imprinted on the CMB as a very specific preferred scale, a standard ruler. We can measure the physical size of this ruler in the baby picture of the universe with incredible precision. And because we think we understand the physics of that early plasma perfectly, we can use this measured size to predict how the universe should have evolved, calculating exactly how fast it should be expanding today. But the prediction fails. The mismatch suggests a terrifying possibility. Perhaps the sound horizon we measure is not the size we think it is. The early universe's expansion history must have been different than our models assume, altering how far those sound waves could have traveled before the music stopped. It is like discovering that a fossilized footprint from a dinosaur, which we thought was from a creature walking at a steady pace, actually came from one that was running. The length of the stride would be the same, but the story of its motion would be completely different. If the infant universe expanded faster than we thought, even for a brief moment, the sound waves would have had less time to travel, resulting in a smaller frozen ruler. Our models, blind to this early speed boost, look at this smaller ruler and incorrectly calculate a slower expansion rate for the modern cosmos. The tension, therefore, is a direct result of a miscalibrated ruler. We are trying to measure the present-day universe with a yardstick from the past that we are reading incorrectly. The very foundation of our cosmic geometry seems to be flawed, forcing us to question not just the expansion, but the symphony of forces that govern the universe's first notes. The numbers themselves are screaming that this is no accident. With every new observation, the statistical significance of the Hubble tension has only grown stronger. It has now soared past the 5 sigma threshold, a landmark in physics that essentially rules out a mere fluke. To understand what that means, picture a coin toss. If you get heads 5 times in a row, you might call it luck. If you get heads 50 times in a row, you start to suspect the coin is rigged. The 5 sigma level is like getting heads so many times in a row that the odds of it being simple chance are less than 1 in 3.5 million. This is the same standard of certainty required to declare the discovery of a new particle like the Higgs boson. The universe is not whispering a hint, it is shouting a contradiction. For the Hubble tension to be a statistical illusion, we would have to be the unluckiest generation of astronomers in history, consistently misinterpreting data from entirely independent methods in the same exact direction, time and time again. The cosmos is simply too consistent in its inconsistency for this to be a cosmic typo. The evidence has moved from a curious anomaly to a concrete crisis. This leaves us with a stark and unavoidable conclusion. The problem is not in our data, it is in our dogma. Every measurement we make is filtered through a fog of cosmic uncertainty. Behind the clean numbers and elegant equations lies a messy reality of astrophysical systematics, a hidden world of subtle effects that could be secretly biasing our results. Think of it as trying to read a street sign through a dirty, foggy windshield. You might still make out the letters, but the grime subtly distorts the message. In cosmology, this grime comes in many forms. There is dust extinction, where interstellar dust floating between stars acts like a cosmic veil, selectively reddening and dimming the light from distant supernova and Cepheid stars. If we underestimate how much this dust has dimmed a standard candle, we will believe it is farther away than it truly is, directly inflating our measurement of the expansion rate. Then there are stellar population changes. We assume a Cepheid variable in a nearby galaxy is identical to one in our own Milky Way. But what if Cepheids born in different galactic environments with different chemical histories age at slightly different rates or have subtly different internal structures? Their famous period luminosity relationship, the very core of the distance ladder, would not be a single universal rule but a family of similar-looking curves. Using the wrong one would be like using a ruler made of rubber that stretches unpredictably, and we cannot forget our own instruments. Every telescope from Hubble to Webb has its own unique quirks and biases. The complex software pipelines that process the raw data, correcting for camera noise and cosmic ray strikes, might inadvertently introduce their own tiny, consistent errors. These are not mistakes, but inherent limitations in our ability to see perfectly. The terrifying possibility is that all of our independent measurement methods could be suffering from different, unknown systematics that all conspire to push the Hubble constant in the same direction. It is not a grand conspiracy, but a confluence of minor biases that together create a major illusion. The tension, then, would not be a discovery of new physics, but the ultimate testament to our own ignorance, a reminder that the universe is far more complex and dusty than our cleanest models can possibly account for. This single number holds the future of cosmology in its grip. Resolving the Hubble tension is not about finding a missing decimal point. It is about choosing between two radically different futures for our understanding of everything. On one side lies the comforting path of confirmation, where a subtle error is found and our beautiful standard model of cosmology is validated, its predictions secure. On the other side lies a revolution, a complete overhaul of our cosmic story. The stakes could not be higher because this is not just about the expansion rate. It is about the very ingredients of reality. Our model tells us precisely how much dark matter should be holding galaxies together, how dark energy should be pushing them apart, and how ordinary matter should be woven through the cosmic web. The Hubble constant is the keystone that locks all these pieces together. If we are forced to change it, the entire arch collapses. We would have to admit that dark energy is not a constant, that dark matter interacts in ways we never dreamed, or that entirely new components, forces we have not yet named, are part of the cosmic recipe. This would redefine the universe's entire life story, from its explosive birth to its final, cold fate. Will it end in a silent freeze, a catastrophic rip, or something we have not yet imagined? The answer depends entirely on which value for the Hubble constant is true. This is why scientists are not just puzzled, they are captivated. This is not a problem to be solved, but a doorway to be opened. What lies on the other side will determine the course of science for the next 100 years. A stalemate this profound demands a new kind of tool. With the traditional methods locked in a fruitless debate, the scientific community is embarking on a global treasure hunt, forging entirely new instruments and techniques to break the deadlock. This is not about refining the old ways, but about inventing new ones from the ground up. One of the most promising avenues is the study of gravitational waves, the ripples in space-time itself. When two ultra-dense neutron stars spiral together and collide, they send a shiver through the fabric of the cosmos that we can now detect. This event is a standard siren. By analyzing the unique properties of the gravitational waves, physicists can deduce the intrinsic strength of the collision. Then, by observing the flash of light that often accompanies it, they can see how dim it appears from Earth. This combination provides a direct, one-step measurement of the distance to the event and the expansion rate of the universe, completely bypassing the entire messy cosmic distance ladder with its Cepheid variables and supernova. It is like being given a single, perfect measuring stick instead of having to chain a dozen questionable rulers together. Another frontier lies at the very edge of observable time, in the era of the cosmic dawn. This was the moment when the first stars and galaxies ignited, ending the Dark Ages and flooding the universe with its first light. New radio telescopes like the Hydrogen Epoch of Reionization Array are trying to map the faint whisper of neutral hydrogen from this ancient period. The pattern of how this primordial gas clumped together is exquisitely sensitive to the expansion rate in the universe's youth. By comparing this adolescent growth chart to the adult universe we see today, we can trace the expansion history with a fresh, independent line of evidence. Every new probe, from the subtle lensing of distant gamma ray bursts to the precise timing of pulsars, is a new voice entering the conversation. The hope is that one of these new voices will finally break the symmetry, clearly siding with one camp over the other, or perhaps revealing a third, even more astonishing path forward. We are no longer just arguing over the old map. We are sending out new scouts to survey the territory afresh, hoping one will return with the key that unlocks this cosmic prison. This persistent crisis in cosmology is far more than a technical disagreement over a number. It is a philosophical earthquake shaking the very foundations of how we know what we know. Science progresses not just by accumulating facts, but by confronting anomalies that refuse to go away. A problem this stubborn, this statistically significant, ceases to be a puzzle and becomes a profound challenge to the scientific paradigm itself. It forces a community of brilliant minds to stare into the abyss of their own ignorance and consider the unthinkable, that their most cherished theories might be fundamentally flawed. This is precisely how every great scientific revolution began. For centuries, Newton's laws of motion and gravity were considered perfect and complete. They predicted the orbits of planets with breathtaking accuracy. Yet a tiny, nagging anomaly persisted in the orbit of Mercury, a wobble that Newton's equations could not explain. Most scientists ignored it or tried to explain it away with ad hoc fixes. But that tiny wobble was a crack in the foundation, a whisper from the universe that a deeper truth was waiting. It was only when Einstein developed his theory of general relativity that the wobble was not just explained, but became a necessary consequence of a new, more beautiful understanding of gravity. The crisis over Mercury's orbit was the catalyst that shattered an old worldview and ushered in a new one. The Hubble tension is our Mercury. Its persistence is a signal that we have reached the limits of our current cosmological model. We are being invited, or perhaps forced, to question our most basic assumptions. Is dark energy really constant? Is general relativity the final word on gravity? Is the cosmological principle that the universe is uniform actually true? To answer these questions, we must be willing to let go of what we think we know. The greatest breakthroughs do not come from confirming what we expect, but from embracing the data that confounds us. This tension is not a sign of failure, but a sign of a field that is vibrantly alive on the cusp of a transformation. What new reality is waiting for us on the other side of this confusion? This cosmic mystery belongs to everyone. The Hubble tension has reached beyond the domes of professional observatories and into the public square, transforming a deep scientific crisis into a shared human adventure. Crowdsourced science projects now invite anyone with an internet connection to join the hunt, sifting through terabytes of telescope data to identify distant supernova or measure the shapes of far-off galaxies. Your living room can become a frontier of cosmology. This massive, distributed effort does more than just process data. It brings millions of fresh eyes to the problem, eyes that might spot a subtle pattern or a strange outlier that a tired, specialized researcher could easily miss. It is a modern-day barn raising for the cosmos, where the collective curiosity of humanity helps to build the framework for a potential breakthrough. This public engagement is not a side effect of the mystery, it is a vital component of the solution. By democratizing the search, we are not just finding more data, we are inviting more perspectives. A retired engineer, a high school student, or an artist might look at the same celestial data and ask a question a lifelong astronomer would never think to pose. The very nature of the problem, a fundamental conflict in our story of reality, resonates with a deep human need to understand our place in the universe. We are not passive observers of this drama, we are all potential participants in its resolution. The final answer to the Hubble tension will not just be written in a scientific paper, it will be written in the collective effort of our species reaching for the stars together. Perhaps the ultimate reason this single number captivates us is the grand prize it might unlock. The Hubble tension could be more than a crisis. It could be the final clue pointing toward a unified theory of cosmic physics, a single framework that solves this and every other major mystery in one elegant stroke. For decades, we have wrestled with a universe that seems to be built from separate, puzzling pieces. We have dark matter, an invisible substance that provides the gravitational glue for galaxies, but we do not know what it is. We have dark energy, a mysterious force accelerating the expansion, but we do not know why it exists. And now we have the Hubble tension, a stark disagreement about how fast that expansion is actually happening. What if these are not three separate problems, but three different symptoms of the same underlying flaw in our understanding? Imagine a master lock with three distinct tumblers. For a century, we have been trying to pick each tumbler individually with specialized tools with some success, but the lock remains stubbornly shut. The Hubble tension is the sound you hear when one of those tumblers, the one governing cosmic expansion, refuses to click into the place our current keys expect. This failure suggests that we do not need a better pick for that one tumbler. We need the true master key, the one single shape that aligns all three tumblers at once. That master key would be a new theory of gravity and quantum mechanics, a framework that seamlessly connects the very large with the very small. It would tell us what dark matter truly is, not as an exotic particle we must hunt for, but as a natural consequence of this deeper physics. It would explain dark energy not as a constant, but as a dynamic field whose strength has evolved, elegantly resolving the tension between the ancient and modern expansion rates. In this grand vision, the Hubble tension is not a mistake, but a precise calibration signal from the universe. It is the cosmos telling us exactly how far off our current model is, giving us the exact measurements we need to forge the correct key. The number that has caused so much frustration could ultimately be the most important number in all of cosmology, the one that leads us not just to a fix, but to a final, complete theory of everything. Are we on the verge of discovering not just what the universe is doing, but what it truly is? 25 threads of evidence now weave together into a single, undeniable tapestry of mystery. It is a crisis born from the clash between our most pristine cosmic fossil and our sharpest modern observations, between the steady beat of ancient stars and the silent ripple of gravitational waves. We have confronted flawed standard candles and the ghostly influence of neutrinos, wrestled with the possibility of a cosmic void and the specter of evolving dark energy. We have seen our foundational models strained to their breaking point and witnessed our most powerful telescopes confirm the problem rather than solve it. Each reason, from the subtleties of interstellar dust to the philosophical challenge to our entire paradigm, is a door we have tried to open only to find another locked door behind it. This is not a single error waiting to be corrected. It is a chorus of discordant data, all singing the same unsettling song, that our map of reality is missing a fundamental continent. The Hubble tension is a gateway. On one side lies the universe as we think we know it, comfortable and complete. On the other lies a cosmos far stranger, governed by rules we have not yet written. This is not the end of the story, but a thrilling new chapter in the greatest detective story ever told. The clues are all around us, hidden in the light of distant stars and the whisper of the Big Bang. The greatest discoveries in science have always begun with a puzzle that refused to be solved. So keep watching the skies and keep listening to the scientists who are piecing this cosmic puzzle together. Your curiosity is part of the search, and the next breakthrough could change everything we know about our place in the universe.